All right, ladies and gentlemen, so chapter 4, part 2, degrees and radians. I'm also going to explain how the rest of the unit circle is developed from what we made yesterday. Yes, ma'am. Sure. Yeah, just try not to make a mess, sir. Poor janitors work hard. Okay, so the task for today is to convert degree measures of angles to radians and vice versa, and use angle measures to solve real-world problems. So some vocabulary: vertex, initial side, and terminal side. These are the three parts of an angle, and I discussed these briefly yesterday. But if it's something you're not familiar with, you should definitely make note of it. So there are three parts of an angle: a vertex, an initial side, and a terminal side. The vertex is where the two rays meet. The initial side is where the angle rotation begins, and the terminal side is where the angle rotation ends. So if I were to sweep out an angle between Colin and Holden, this would be ray 1, this would be ray 2, and my body would be the vertex. All right. So standard position is when you have the vertex at the origin, and then a radian is a unitless measure of rotation. This is awesome terminology. So, coterminal angles, and this is probably something you should make note of because we haven't talked about it at all yet. Angles that share a terminal ray. So, remember my example where I said if I swept out an angle between Colin and Holden, is that the only angle possible that lands on Holden? No, I could go all the way around. I could go in a negative angular direction. So, there are a lot of angles that share a terminal ray. We call those coterminal angles. Linear speed, this is speed of rotation in terms of arc length. Angular speed is speed in terms of angle. There are two fairly challenging test questions on these two topics. So those are these two represent topics that are often missed on the test. And then the last definition here is sector. It's a part of a circle, and we're going to measure it with a formula, but think slice of pizza. So if the circle were a pizza, the sector is like a slice. I'm always going for that big slice. I don't know about you guys. You better save that big one for me. Or we fix it with our hands. Man, we done tore that coffee up this morning. Having a coffee pot in your room is like having a swimming pool at your house. You're just all of a sudden real popular. Everybody likes you. So come visit. Yeah, man. Okay, so any questions about any of these terms? So what I'm going to do now really quickly is build the rest of the unit circle based on what we learned yesterday. You can sketch it if you like. I used to hand out fancy copies, but They don't want us to hand a lot of stuff out this year because we give you COVID. All right, so we're going to have 3 rays in each quadrant, and they should kind of look like this. And I'm not worried about this being perfect. Mine won't be perfect, even though I've got the advantage of a straight line tool. As long as you understand what it means. Okay, so the first thing you want to do is populate all the angle measure information. So 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. And then into quadrant 2. So you should probably also label the quadrants. They go counterclockwise. Like so. 1, 2, 3, 4. And then in quadrant 2, 120, 135, 150, 180. Then into quadrant 3, we've got 210, 225, 240, 270. Then into Q4, 300, 315, 330. And then also often we put 360 here. So those are all the degrees from the unit circle. Now we remember the points. We already found some of these points yesterday. 1, 0, square root of 3 over 2, comma 1/2. Square root of 2 over 2, comma square root of 2 over 2. And then 1/2, comma radical 3 over 2. And then 0, comma 1. So those represent the corresponding points. Now, every other point on this unit circle can be found as a consequence of symmetry. You know, circles are symmetric to the x-axis and the y-axis. Let me see if I can enlarge this a little bit so you guys squinty. So circles are symmetric to both the x and the y-axis. So there's symmetry about here and about here, which means if this is 1/2 of a unit away from the origin, so will this be. So I know the x value is -1/2, and the y value is the same. So 120 is -1/2, comma square root of 3 over 2. 135 is negative radical 2 over 2, comma radical 2 over 2. 150 is negative square root of 3 over 2, comma 1/2. And then finally 180 is -1, comma 0. And just to remind you, every point is the cosine of that angle for the x coordinate and the sine of that angle for the y coordinate. There we go. Now down into Q3 here. So we've got symmetry here across the y-axis, but everything's negative in Q3. So this is going to be negative radical 3 over 2, comma -1/2. For 225, negative square root of 2 over 2, comma negative radical 2 over 2. For 240, -1/2, comma negative radical 3 over 2. And then finally, in Q3 for 270, I've got 0, comma -1. And all these can be found with the symmetry of the circle. I need no more calculation. 300, so now we're into the quadrant where the x is positive and the y is negative. Symmetric about the y, symmetric about the x. I can use any of these points to help me understand what they should be. So this is going to be +1/2, comma negative radical 3 over 2. This is going to be positive radical 2 over 2, and then negative radical 2 over 2. For 330, I've got positive radical 3 over 2, and and then -1/2. So that's every angle measure in degrees and every value on the unit circle. So we can build it all from that first quadrant. Now, one additional bit of information I haven't taught you yet is the radians, how to convert them. We're going to learn that today. And then we'll go through and populate all these with the radian measures. So that, ladies and gentlemen, is the unit circle constructed from scratch. If you can do this, you never have to memorize it. Now, it's tedious. It takes a lot to learn it. But once you've learned it this way, you never have to memorize it because you can derive any value from scratch that you need. And it's a handy skill. Trust me, it's one that I lacked when I came out of high school. I was totally unfamiliar with the unit circle, had never even seen it. And I went into that Calculus 1 course at ETSU, and all the Dobbins Bennett's and the Science Hill kids, they do it inside and out. I had never seen it, so I was at a distinct disadvantage. One that I would spare you guys if I could. But I would say, learn quadrant 1, memorize quadrant 1, learn how to derive every other value from quadrant 1. You'll never have to memorize it. Okay, we ready to move on? So the first example here, write 329.125 in degrees, minutes, seconds. Well, first of all, let me give you just a brief overview of what degrees, minutes, seconds is, because you probably have never heard of that. So this is an arcane way to subdivide decimals. Remember I told you the Babylonians had a base 60 number system? And vestiges of that ancient system manifest in our modern world. Here is just such an example. For some reason, in nautical applications and aeronautical applications, in other words, on seafaring vessels and air vessels, they use this frequently. So if I were to show this to Dan Mills, he would instantly know what I was talking about. So degrees, minutes, seconds. It's a way to subdivide degrees. So you've got a degree. You know what that is. I have a number, and that's a degree. Now, a minute is 1/60th of a degree. So I'll have y minutes, and it's 1/60th of a degree. And then I'll have so many seconds, we'll call it z seconds, and z is 1/60th of a minute. And that is a degree divided by 60 squared. So I've got some number of degrees, some number of minutes where the minutes are 1/60th of a degree, and then some number of seconds where the seconds are 1/60th of a minute. And it's still used in astronomy. You know, like if they describe the method of parallax, you familiar with this? I can show you real quick. Hold your thumb out and then close one eye, doesn't matter which, and cover something with your thumb. Now, open the other eye and close the one that you had open. What happens to your thumb? It jumps. So that jump is called a parallax, and it's how we measure the distances to near stars. And they use the angle measure, and it's often in something called picoseconds, which is a billionth of a second. So it's nothing you would observe with your eye. You need a very sophisticated instrument. Anyway, degrees, minutes, seconds. Let's apply it here. We're going to rewrite this in degrees, minutes, seconds form. So this is in decimal degree form to begin with. So the standard form you're familiar with is called decimal degree form. 329 degrees. That part's easy. Now the 0.125, I need to convert that to minutes. And the way I'm going to do that is multiply it by 60. So 0.125 times 60 is 7.5. So multiply by 60 the decimal part. And that's 7.5. So I take the 7, and that's the number of minutes. And then I take the decimal again, which is 0.5 in this case, and I'm going to multiply that by 60 to get 30. And that's how many seconds I have. And a good way to test yourself, whether you did it right, is to punch in 329 plus 7 over 60 plus 30 over 60 squared, and see if you get back to that original value, and we do. So that confirms our result. Degrees, minutes, seconds. Often used to describe changes in course for a naval vessel or an aeronautical vessel.
So where did you get the 11?
I'm sorry, Rachel?
The 11?
No 11. It's a double tick mark.
Oh,
I thought it was 11.
Yeah, double tick mark. So remember that the symbol for minutes is a single tick mark. The symbol for seconds is a double tick mark.
I thought that was meant to be like 1 out of something.
Nope, a single tick mark, or minutes rather, I'm sorry. Somebody said that backwards a second ago. Single tick mark is minutes, double tick mark is seconds. Say again, sir? Yeah, there's a lot of overlap, and a lot of inferring from context. The Babylonians were big on that. They had no radix point. In other words, they had no indicator of what power of the base value they were referring to. So if I said I wanted to buy, and the way their number system worked, they had this symbol. That was 1, but it could also mean 60. But it could also mean 60 squared. Or it could mean 1 over 60. So there was no, it was all inferred from context. So if I say I want to buy this many wives, probably talking about 1. If I want to say I want to buy this many barrels of grain, maybe I'm talking about 60. If I want to say I want to buy this many arrows, well, maybe I'm talking about 60 squared. They also had a value of 10, and it looked like this. So this would be 11, or 11 times 60, or 11 times 60 squared. A lot of inferring from context. That's why the Babylonian number system is so difficult to decipher. And it was deciphered by a math teacher, high school math teacher. So they had a tablet, an ancient tablet in clay. Some kids' math homework, but they didn't know what it was. It's just complicated symbols. So a math teacher, high school math teacher, walks by and says, "Yeah, it's multiplication tables." And they were like, "Wait a dang minute." So, and from his statement, they figured out the Babylonian number system, which was up to that point lost to history. Because the Babylonians were not good at fighting. They got their butts kicked. And the civilizations that lost wars were the ones that were lost to history. Only the winners persisted. Why do you think we remember the Spartans so well? Or the Greeks? The Greeks had an extremely formidable navy, and the Spartans an extremely formidable army. So together they were pretty unstoppable. Especially in the form of Alexander. He basically took over the world. So now we're going to start with decimal degree. I'm sorry, start with degree, minutes, seconds, and go to decimal degree. Pay attention, Jesse. Play with Colin until after class. So what we've got here is 35 degrees, so that's easy enough, plus the minutes are going to be divided by 60, plus the seconds are going to be divided by 60 squared. So we just punch this in our calculator. 35 plus 12 over 60 plus 7 over 60 squared is, and this is round to the nearest thousand, so that's going to be 35.202. So this is one you really, and it's a degree. This is one you really shouldn't miss on a quiz or a test. And you're going to see it on both. So, rip if you don't get this. Because this will likely be the easiest one on that quiz or test. Like a little softball, confidence builder. Here, hit this one. All right. So here's one for you. Write this one in degrees, minutes, seconds for me, please. So this is like example 1, part A, the very first one we did. Give you about 30 seconds to do this one, so you shouldn't need longer than that. All right, Ian, tell me what goes right here.
16.
Very good. Well, just 16. The 0.5 we use on the next step. And then Bristol, tell me what goes here.
30.
Very good. Excellent work, gentlemen.
What do you end up not doing the whole number?
You would round to the nearest second. So on that very final step, you should round to the nearest second. Good question. You won't have a decimal. Now, you know, like I said, there are things like nanoseconds and picoseconds, but we're just going to round to the nearest second. Rachel?
So, are we supposed to go ahead and get the wait, I'll just do it.
So you're going to multiply 0.275 times 60, which gives you 16.5. So the 16 comes from there. The 0.5 times 60 is where the 30 comes from. So take the decimal part of the degree, multiply it by 60, take the whole number part of that, and that's your minutes. The decimal that's left over, multiply by 60 again, and that's your seconds. All right. Now let's talk about Radian Measure. So this is something we went over pretty exhaustively yesterday, but no, this is available in your text if you need reinforcement. Conversion factor. So now we're talking about something kind of new. So to convert a degree to radians, your conversion factor is pi over 180. To convert from radians to degrees, your conversion factor is 180 over pi. And you'll be doing these primarily by hand because your calculator will give you a funky decimal if you try to use pi. So when I go from degrees to radians, I multiply by pi over 180. When I go from radians to degrees, I multiply by 180 over pi. So very important. Once again, this will be a quiz and a test question. One you absolutely should not miss. All right. So write 135 in radians. So 135 degrees, I need to multiply that by pi over 180 because we're going from degrees to radians. So the result is 135 pi divided by 180, which of course reduces. 45 is your reduction factor. So 135 is 45 times 3, and 180 is 45 times 4. So this is 3 pi over 4 if I divide top and bottom by 45. Now you can use your calculator for the reduction part, if you're cautious and you don't use the pi bit. So if I go 135 divided by 180, and then I hit math, enter, enter, it's going to give me the least fraction represented by that ratio, the fully reduced fraction. So it's math, enter, enter. Converts whatever you put into it to a fully reduced fraction. If you suck at this part, be conscious of that capacity of your calculator. All right, what about negative 30? So we're going to multiply that once again by pi over 180. And so I get negative 30 pi over 180. Remember, positive angles go this way, and negative angles go this way. Why? Well, that's just what we decided. No special reason for it. Counterclockwise is positive, clockwise is negative. If I divide top and bottom by 30 here, I get negative pi over 6. And again, notice there's no unit attached to the radian. How do I know that's a measure of deflection? Well, because the pi is there. And so if you see a pi in the wild, that's probably a radian. Questions about anything? All right, cool. So what about 2 pi over 3 as a decimal, or as a degree, right? 2 pi over 3. We're going to multiply that by 180 over pi, because we're going from radian to degree this time. Conveniently, the pi's will almost always cancel. And so 2 times 180 is 360 over 3 degrees, which is 120 degrees. So at this point, you should be able to write a degree, a partial degree in decimal degree form or degree minutes seconds form. You should be able to convert between degree and radians. That's what our tasks are so far today. I think there's one more here. Negative 3 pi over 4. Once again, we're going to change to a degree. It's currently a radian. So in order to change to a degree, I multiply by 180 over pi. Once again, conveniently, the pi's cancel. Negative 3 times 180 is negative 540. And then that's going to be over 4. And 4 goes into 540. 135 times. So that is negative 135 degrees. Okay, so let's pause here and go back to our unit circle for just a moment, because we're now ready to include those radian measures. So for 0, it's 0. For 360, it's 2 pi. Those are pretty easy. For 30 degrees, we already found that one. That's pi over 6. 45 degrees, well, if we multiply that by pi over 180, that's going to be pi over 4. For 60 degrees, that's going to be pi over 3. For 90 degrees, that's going to be pi over 2. For 120 degrees, that's 2 pi over 3. For 135 degrees, that's 3 pi over 4. For 150 degrees, 5 pi over 6. And then 180 degrees is just pi. So that's the upper half of the unit circle, all the degrees converted to radians. Say that again. Well, it's going to be messy. It's going to be messy, but
I don't know.
there's just a lot of stuff to write. Okay, so going into Q3 here, this is 7 pi over 6. And here I have 5 pi over 4 for 225. For 240, I got 4 pi over 3. And for 270, 3 pi over 2. So that's Q3. All right. So 300 is 5 pi over 3. And for whatever reason, Q4 is the one most people screw up. I don't know exactly why. I guess they're a little more complicated, less intuitive. 315 is 7 pi over 4. And then 330, our last one, is 11 pi over 6. Sorry, not 12. Or 11 pi over 6. All right, so there in green you have all the radian measures for the unit circle. And once again, if you learn how to derive these and calculate this, you don't have to memorize anything. Get on the fly, sum in that calculation. Which again is kind of the way I had to do it because I had never seen it before. When I went to Calculus 1 class. Okay, so let's talk now about converting. So I want you guys to try this one. Write 150 degrees as a radian measure. That was one of the values on the unit circle, so it should be super easy. Thank goodness it's Friday. Oh yeah. It's gonna be a rainy weekend though. It's kind of a bummer. Yeah, test is due this evening. We haven't tackled that yet.
I get it done before.
Good luck. Okay, so Holden, tell me what the 150 degrees is in a radian measure.
Hot times.
Very good. So those are the kind of calculations you should be able to just really quickly rattle off for me. So coterminal angles. For any angle alpha, if I add 360 n degrees, where n is a real number, then we're going to have, well, actually, integer is what I mean to say here. Where n is an integer, you're going to have a coterminal angle. If you're dealing with alpha in radians, it's going to be alpha plus 2 pi n, where n is an integer. So when you're dealing with degrees, it's going to look like the top one. When you're dealing with radians, it's going to look like this one. That's how we find coterminal angles. How many are there? Well, how many integers are there? If I start counting, how many numbers are there going to be?
Infinite.
Indeed. So there's an infinite number of coterminal angles. However many times you're willing to spin. You know the old joke about the Xbox 360, you turn 360 degrees and walk away. Well, you could also turn 720 and walk away. Which would be difficult because you're facing it, but whatever.
Yeah, I was about to say.
It was a meme that was meant to confuse the mathematically uninitiated. Or just be nonsensical, as so many memes are. Okay, so let's do some coterminal angle work. Identify all angles that are coterminal with 80, and then find one positive and one negative and draw it. First of all, let's sketch 80 degrees itself. So 80 degrees is just less than a right angle. So it's going to look something like this. Now, for every coterminal angle, that's going to be 80 plus 360 n degrees, where n is an element of the integer. So this is every possible one. And they say find one positive and one negative. Well, the easiest positive one is to let n equal 1. So this is our positive coterminal angle. I'll let n equal 1. So this is 440 degrees. And 440 degrees is going to look like this. And then one negative, they said. So let's let n equal negative 1. So that's going to be 80 plus 360 times negative 1 degrees, which is negative 280 degrees. And that's going to look like this. Now, go all the way to the terminal ray. They all share the same initial and terminal ray. The difference is the angle being swept out. So again, the answer, 440 and negative 280, and then this sketch. So some of the homework questions ask for the sketch. The sketch is part of it. You don't do the sketch, you're not really understanding. You can do that calculation and not understand how it connects to the actual angular rotation. Like a parrot when it says, Polly want a cracker. Doesn't know what those words mean. You know, it knows that if it says it, it gets a treat. Well, I say that some birds are highly intelligent. It may actually know a little bit more than we think.
That is the closest human bird that we are.
We got a visceral hatred for birds. Something about their reptilian eyes sparks a race memory in me of my little mammalian ancestors scurrying from the dinosaurs or something. Okay, so coterminal angles with a radian measure. Identify all angles that are coterminal with negative pi over 4. That's going to be negative pi over 4 plus 2 pi n, where n is an element of the integers. Once again, I'll sketch it before I do any of this other stuff. So that is 45 degrees in a negative direction. Looks something like this. So that is negative pi over 4. We want one positive and one negative. So for the positive one, I'm going to let n equal positive 1. So that's going to be negative pi over 4 plus 2 pi. We need a common denominator. So that's negative pi over 4 plus 8 pi over 4, which is 7 pi over 4. And he's going to look like this. So that's a positive coterminal angle. For the negative one, let's let n equal negative 1. And so that's going to be negative pi over 4 plus negative 2 pi. Once again, we need a common denominator. Negative pi over 4 minus 8 pi over 4 is negative 9 pi over 4. And that one, let's see here, is going to be difficult to draw on top of all this other stuff, but try here. Hopefully that mess looks decipherable. So we have a positive and a negative coterminal angle. But how many total coterminal angles are there? Say again? Infinite, indeed. So there was no end to them. I can make as many as I like, and a list from now till the end of my life if I chose to do so. It would be a ridiculous choice, but I could make. Here's one question, Rachel. Sure. Okay, no problem. Here's one for you guys. One negative and one positive coterminal angle to 126 degrees. Sketch it as well. Then Q2, if that helps you. Creating one positive and one negative coterminal angle. Okay, Rowdy, tell me what your positive coterminal angle is.
206.
So that wouldn't quite do it. Let me show you why. So we've got 126 here. 206 would be like somewhere over here.
No, I know that didn't.
It's okay. So what we should do is,
Should be 486.
correct. And then tell me what your negative coterminal angle is, Jesse.
Negative 234.
Let's double check you here. Negative 234, very good. All right, so that's an example of a positive and a negative coterminal angle. And they would look like this. The positive one would go all the way around and land back there. And the negative one would be like that. So arc length is a formula given by S equals R theta. Very important formula. This angle, the angle theta, must be in radians. So angle theta must be in radians. So R is the radius. And then S, of course, is the arc. Go ahead, buddy.
So S is the circumference.
Say again, sir?
So S would be a part of the circumference of the circle.
Indeed, a portion of it.
Covered by the angle.
Yeah, whatever's swept out by the angle theta, that part of the circumference of this circumscribed circle. But it's, you know, the circle is just a visual aid. This is the angle. And it sweeps out the arc. It is a part of a circle with that radius, though. Yes. Good observation. All right, so let's find the arc length. Find the length of the intercepted arc in a circle with a central angle measure of pi over 3 and a radius of 4 inches. So we'll just draw this to help us. So we've got in this circle a radius of 4 inches. And we're concerned about the arc swept out of an angle pi over 3. So we want to know how long is this arc. I hate the way it does it. How long is this arc is the question. So we're going to use S equals R theta. So S equals 4 times pi over 3. 4 pi over 3. It's just round to the nearest tenth. So 4 times pi divided by 3 is about 4.2 to the nearest tenth. And we're in inches. So about 4.2 inches. Fun fact, do you see how that's almost the exact same as the radius? You see how that's because pi over 3 is almost 1? So it's almost 1 unit of radian measure. All right, so simple application of the arc length formula. What if we had 1 in degrees here? So same sort of problem, but this time they throw a few additional obstacles in our path. So we've got a circle with radius of 7 centimeters. We've got an angle measure of 125 degrees. It's going to be something like this. And then I have S equals R theta. So, Colin, why can't I just plug in 125 for theta? Indeed, and it must instead be in radians. So we got to convert 125 to radians first. So 125 times pi over 180. If I reduce that fully, 125 divided by 180, math, enter. 25 pi over 36. is the fully reduced version of that angle in radians. So S equals 7 times 25 pi over 36. And we're going to approximate that to the nearest tenth. So we multiply this times 7 times pi, we get 15.3 to the nearest tenth. And it's in centimeters this time. Don't forget your units at the end. So finding the arc, ARC. So now you should be able to convert between decimal degree, degrees, minutes, seconds, convert between degree and radian. You should be able to find coterminal angles. You should be able to find arc lengths. That's where we're at. You got a couple more things though. All right, so linear and angular speed. I've got two formulas, and they're both important, they're both worthy of note. These are those test problems that are frequently missed. So I've got linear speed. I'll just write it down here. Linear speed at the R point from an angle is given by V equals S over T, where S is the arc length formula that we just learned. And V is the velocity, and it's given by the arc divided by the time. T is in time. And then the angular speed is given by the Greek letter omega, which is fun. It looks like a funky W. And it's equal to theta over T, where theta is in radians. Yes. So linear speed, V equals S over T, where S is the arc length. Angular speed, omega, equals theta over T. All right. Let's apply those. So a typical vinyl record has a diameter of 30 centimeters. Diameter. You know, we deal a lot with radius, so we have to be conscious of that potential problem. When played on a turntable, the record spins at 33 1/3 revolutions per minute. Find the angular speed in radians per minute of a record as it plays. So angular speed is what we're concerned with. We got a red herring in this problem. In other words, information we don't need. Remember, that's just theta over T. So we don't need the diameter for this problem. This is a red herring. In other words, meant to distract. 33 1/3, we're going to multiply that by 2 pi to get the total theta. So this is going to be the angle swept out per minute. 33 1/3 times 2 pi. So round to the nearest tenth, it says 33.3. We'll just do to the nearest hundredth here so we can round with certainty. Times 2 pi. It's about 209.4 radians per minute. And that's because omega is equal to theta over T, which in this case was 33.3 times 2 pi over 1 minute. This is a distractor in this problem. We'll need it in subsequent problems, but for this problem, the diameter is only there to distract you. Okay, so same scenario. What is the linear speed in centimeters per second? So we've got some unit conversions to make here. And this is the reason why it's so often missed on the test, because there's a unit conversion that people don't notice. So we got this speed in minutes, and they want the answer in seconds. So the speed in minutes, this is per minute, is 33.33, that's close enough, times 2 pi, and that's per minute. Do you see how we'd have to divide that by 60 to get the speed in radians per second? Because to convert from minutes to seconds, we divide by 60. So we divide by 60 to account for that seconds. All right, so our velocity equals S over T, which is R times theta over T. R is 1/2 of 30, so 15 times, and then whatever that value is. So 33.33 times 2 pi, and then divide that by 60. About 3.5 over 1 second. So 15 times 3.5, about 52.4. And that's in centimeters per second.
Where did you get the 15 from?
So,
Oh, the radius. No.
yes, so the diameter is 30,
Right.
so the radius is therefore 15.
Okay.
That's okay. Good question. Yeah, the units are what throw people here. I think the one on the test, if I remember, it's inches and feet, maybe inches and yards, something like that. Similar idea. Okay, so I think it's worth doing another one of these. So find the angular speed in radians per minute of, if the diameter is 6 feet of a carousel. You ever ride these at Dollywood or whatever? So it rotates at a rate of 10 RPMs, revolutions per minute. Angular speed per minute, so we don't need to convert into units here. This is a red herring in this problem. So it's 10 times 2 pi, or 20 pi. So that's the theta. And remember that omega equals theta over t. And here the t is just 1 minute. So that's 20 pi over 1. And they don't tell us to approximate, but we will just for consistency's sake. 20 pi is about 62.8. And that's in radians per minute.
So what is the purpose of knowing the angular speed? Radians or
Well, let's say you're developing that carousel. Do you see how the linear speed is not going to be relevant for the central motor that drives the carousel? You're only going to care about how many degrees it sweeps out. So regardless of how far you are from the center, that angular speed is the same. So setting the RPMs of that central motor would require you to understand the angular speed. So there's a lot of engineering applications.
Fair enough.
And I'm not an engineer, so I can't give you all of them, but that's just one that occurs to me.
So where did you get?
So it says per minute. So that's per 1 minute. And that's a little confusing, but yeah, per 1 minute makes that part kind of trivial to the point where you're like, wait a minute, I'm missing something. But no, it is actually that trivial. Area of a sector. Remember I told you guys this would be like a slice of pizza? This is a big old slice right here, right? This is a Chad size slice. That's what, I didn't exactly eat healthy when my kids were growing up. You know, it's just a busy time in your life. So my daughter Mindy, you guys know, if you know her, you know she's a tiny little person. She's student teaching at Eastside Elementary this year. But we would get a Little Caesars pizza on the way home, and it would be gone before we got home.
Oh, yes. That's not that much pizza.
Yeah.
I eat a whole Little Caesars pizza.
Yeah.
It's like a $5 pizza.
Yes.
I eat all of it.
Yeah. It's the best food deal in the world.
It really is.
Might not be the best, but I mean, best.
I had a friend, he's currently went on a big time diet and lost down to a healthy weight, but he was in the upper 400s at one point. Real cool guy. I went to high school with him. Interesting guy. He's a radiologist, so he studies X-rays and so on. So he's got a great job, makes a lot of money. But he would eat every meal. He would eat a whole Little Caesars pizza and drink a 2-liter of soda.
Oh, my.
So he started calculating his calories per day, and it was on the order of 10 or 15,000 a day that this cat was eating. And he went from that to a zero carb diet and lost all of. Yeah, I think he weighs about what I do now. So he's lost a ton of weight.
Casual, yeah. 6 liters a day.
Yeah, he would do that. Okay, guys, quiet please. The area of this sector is 1/2 r squared theta. And as has been the case for all these examples, theta has to be in radians. So we need radian measures for these formulas to work. You stick a degree in here, rip. 1/2 r squared theta, area of a sector, slice of pizza. Find the area of the sector. This is a little small, so let's get large. So I've got A equals 1/2 r squared theta. So that's 1/2 5 squared times 3 pi over 4. And that's going to be in meters squared. So 0.5 times 5 to the second power times 3 times pi divided by 4. 29.5 to the nearest 10th. Is that what they want here? Yes, goodbye. Any questions about anything we've talked about? So we have covered a lot of topics, but I would hope they were well within your intellectual grasp.
That's what I'm hoping.
All right, so here's one where they kind of throw a little curveball at us. We've got a degree measure here, but 60's on a unit circle. I can convert that real quick. That's pi over 3 radians. So the area equals 1/2 8 squared times pi over 3. And that's going to be in square feet this time. So 1/2 times 64 times pi divided by 3 in feet squared. We'll put it in our calculator this way. 0.5 times 64 times pi divided by 3. About 33.5 to the nearest 10th. Okay. And that's chapter 4, part 2. Let me give you the briefest of brief assignments here. So your task is to complete Page 238, 2 through 16 even, and then also 33. Oh yeah. 238.